natural software, which is DNA, I'm going to look at something much simpler where I can control what's going on, which is to see what selection will do applied to random mutations on artificial software, which are computer programs.
By random mutation, you mean in the generality of the algorithmic complexity theory?
No, I mean random in the sense of statistical physics. Right. So these are probabilistic models in which I have a probability distribution on all possible mutations, and I'm going to be talking about how you do that. And this field, if it's is in very early stages. I like to call this field metabiology. So to define it formally, the proposal for metabiology is metabiology is not theoretical biology. It's not like theoretical physics. It's a little further away from the real subject. So metabiology is a field parallel to biology, which instead of studying the result of random mutations on natural software, which is DNA, it studies the result of random mutations, evolution due to random mutations on artificial software, which are computer programs, with the idea of being simple enough that you can either prove rigorous theorems or at least carry out the kind of heuristic arguments that are used in theoretical physics, which don't satisfy a pure mathematician, but which all of us who know and love physics know are very convincing arguments, even if they're not the kind of rigorous arguments that a pure mathematician would want. And we have a few examples of versions of models of this kind where we can actually prove theorems. Professor Martin-Delgado has one in a quantum version of this, using quantum computing, quantum information, and I have two models using ordinary computer programs and this kind of program size complexity. And the hope is that the idea is, what is biology really all about? It's about information. And what kind of information? Well, there are a lot of information theories. There's Boltzmann entropy, there's Shannon entropy, there's qubits, and there's this notion of program size complexity, of algorithmic information. And my suggestion is that for biology, algorithmic information is not exactly what's going on in biology, but it's the closest of the four that I mentioned. Because DNA is essentially an algorithm it gives instructions for generating the organism and for running the organism. So it's not an exact match, because no theory is ever an exact match for the actual phenomenon, which is much messier. But I think it's the closest match in the toolkit we have at the current point. So the idea is to show that you can go a certain direction, you can go a certain ways in this direction and come up with theorems, and the hope is that this will be the beginning maybe of a kind of a theoretical biology, but I would call it theoretical metabiology, because at this stage it is dealing with, it's a little bit removed from the real biology, because DNA is a very complicated programming language that we don't really fully know. So instead of trying to deal with that, we're working on toy models with programming languages which we do know because we invented them. So that's what the rest of the week will be about. I'm going to give a conceptual sort of talk about biology tomorrow, which doesn't need this today's talk. This is the sort of the historical context this comes from. And then on that's Tuesday. Wednesday will be trying to give a sketch of how you prove the main results in the model that, as a pure mathematician, I find the most interesting. And then I wish you were giving a talk on your model, but I have your paper, and I want to talk to you about it. And then on Thursday, Virginia will talk more about some methodological considerations, a history of ideas from a philosophical point of view. So we're hoping that maybe if we combine efforts between Brazil and Madrid and Sao Paulo maybe also, that maybe these ideas can be developed, and it's not to say that all the theoretical work that's been done in biology up to now isn't splendid work, but this looks, some of us feel like a promising direction which has not been exploited, in which you can study some biological questions which cannot really be addressed in the existing approaches such as population genetics. So that would be the hope. Okay, so thanks very much.
So this is a normal lecture, so you may now give some questions.
Throw tomatoes.
Yes. Yeah, Professor Galindo?
Yes, sir.
Yes, I have a couple of questions. The first is, how would you rank physical theories according to their complexity, the existing physical theories?
Well, you would have to write it out as a computer program, and a program that calculates what data? Well, it would be the sort of the time history of the physical universe up to now. So if you consider, if that can be represented as a finite string of zeros and ones, so in other words, I would say you would have to program the physical theory to calculate the actual time evolution of a physical system. And then you look at the size and bits of that program. And that includes, by the way, the initial conditions as numerical constants.
But I wonder whether this, the theory of everything, will have complexity infinity.
Well, in mathematics, yes. The theory of everything for pure maths provably would have to have infinite complexity. But, you know, I mean, you see physics students going around with equations on their T-shirt. I guess there's still those of us who hope that at least fundamental physics, you know, this actually is discussed by Leibniz in paragraph 5 of the Discours de Métaphysique. What he's saying is that the world is comprehensible. He's saying the reason that science works is because God has created a very diverse, rich world, but starting from using a very small set of concepts. So the world looks very complicated and rich, but it actually can be calculated from, is what I would say now, is the consequence of a very small set of simple, beautiful ideas. So that's because God is a beautiful artist who creates a beautiful universe. Nowadays, we would say this is the idea that the world looks very complicated, but is actually very simple. It's the product of some very small number of basic ideas. And theoretical physics up to now, I mean, there are phenomenological areas like nuclear physics maybe, or particle physics, but now there are theories for that too. I don't know how well they work. But certainly if you look at Newtonian physics, Maxwell's equations, the Schrödinger equation, Einstein's field equations, these are beautiful, simple equations. Condensed matter already starts to get more complicated, but still it does look like the physical world can be understood pretty well starting from some simple ideas. But it may be that the physical world is infinitely complicated, who knows? But in the world of pure math, you can prove that there is no theory of everything. I just proved it.
And my second question, if I have the time.
Yeah, sure.
The second question relates, in this metabiology you are creating, is there a place...
Hoping to create, yes.
Okay. Is there a place there for the cellular automata, or something like the game of life? Conway?
Yeah, this is all splendid stuff. The intentions are different here. That work is a sort of a toy world in which there are self-reproducing creatures. You know, von Neumann's cellular automata world, where he has a self-reproducing computer, or Conway's version of it. Yeah. They want a toy model, a toy world, a simulated world that you can run on the computer with creatures that self-reproduce. And ideally, you would also like to see evolution taking place. Thomas Ray, I think, Tierra was the model that worked best that I know of for showing some kind of an ecology emerging. But I'm not interested in toy models to be run on a computer. I'm interested in proving theorems. So the intention is a little different. Now, another way to put it is there is no toy, as far as I know, there is no toy model of evolution that you can run on the computer where you can show that evolution takes place indefinitely. They always stagnate. They stagnate when the organism becomes well adapted to its environment. In Tom Ray's world, you got, he did a version where, for the Japanese, where he had done an original version which looked very interesting. You got parasites and hyperparasites. And then the Japanese said, well, come over here, we're going to give you all the resources you want, do a really serious experiment. He did a really serious experiment and nothing happened. What basically happened was he put in a seed organism, and instead of getting more complicated, things simplified, because it turned out that there was a much simpler organism which was very good at copying itself and self-reproducing. And this just took over, and that was the end. So I think what people told me at the Santa Fe Institute in January, James Crutchfield, who seems to know what's going on, I asked him, does anyone have a computer model of evolution which really seems to show evolution continuing, or do they always seem to stagnate? And he said there was no model that looked like evolution would go on. They all seem to stagnate. Well, this is a model that you can't run on a computer. I can prove theorems about it. But I can prove that evolution, in some cases, I can prove that evolution is going to go on forever.
You proved
yeah.
The lectures.
This is going to be, this is going to be the next two lectures.
And this is what you said in the beginning, that you found unsatisfactory in the evolution from a mathematical point of view. This is what...
Right, I think there should either be a proof